Hello everyone, my name is Diego Perez. I have worked with Tomás Ropars and Esteban Meneses, and this will be the presentation of our paper called On the Detection of Silent Data Corruptions in HPC Applications Using Redundant Multithreading. Okay, so what is the problem? This is a current microchip. It's a complex system, and sometimes external causes such as sun radiation might impact the chip and cause a bit to flip. Bit flips. So what that means is that the final result of a calculation might be totally wrong, might be corrupted, and the user can be completely unaware of this issue. That is a silent data corruption. So this is not too frequent for a regular personal computer, but if we increase the scale and we move to a data center, this problem becomes more and more risky, more and more dangerous. So what is usually done to deal with these bit flips is to have some sort of replication. Do the calculation twice and verify if they are both the same. One category of this approach is to replicate at the process level, to replicate the whole process of the application. And if the sibling processes have a difference in their outputs, that indicates a silent data corruption. This is a reliable technique, but it doubles the amount of resources required. So the data, the calculations, and the network communications. So that is a lot of overhead. So contrary to that, there is thread replication, in which the replication happens at the thread level. And it replicates the computations, but not the data. So it's supposed to be cheaper. But because it does not replicate the data, it has to assume that the main memory is reliable. And the main technique within thread replication of this paper, the one that we focus on, it's called redundant multithreading, in which there are two threads that are used to detect silent data corruptions. Okay, so what are our contributions? We propose 3 improvements to redundant multithreading. And the first one is to use simultaneous multithreading for soft error detection. And there is two more of them that focus more on reducing the amount of data exchange. One is called variable aggregation and the other one is called selective checking. We have an evaluation in which we measure the trade-off of these improvements regarding performance versus reliability. And we show that for some HPC applications, the overhead can be as little as 1.1 times, which is quite desirable for a replication technique, while still providing a good error detection. Okay, so what is redundant multithreading in more detail? As I said, there are 2 threads used for error detection. One is called the leading thread and the other one is called the trailing thread. They can also be called producer thread and consumer. So this is what it looks like. The left one is the main thread, and these 2 are the leading and trailing thread. And they are practically the same with some differences. On the producer thread, or the leading thread, after every computation there would be a produce operation, and on the trailing thread, after every calculation, there will be a consume operation. The trailing thread will check if the value that it calculated and the value that it got from the producer are the same, and it's going to send a signal back to the leading thread informing that everything is okay. After that, the leading thread is allowed to continue. And because this is a thread level replication, this comparison needs to be made before this writes to memory. Okay, so something very important within redundant multithreading, it's what it's defined as a volatile memory access. A volatile memory is one that may be modified in ways unknown to the implementation. That means a variable that escapes the thread local scope. It pretty much means all those writes to memory. So in HPC applications, for example, an example would be all the MPI function calls, which are typically used in HPC applications. And a wrong execution on these operations can lead to a catastrophic and irreversible state. So we have to be sure that everything is okay before doing these risky operations, these volatile memory access points. So there are different communication patterns between the threads for redundant multithreading approaches. The first one is called synchronous, in which both threads execute synchronously. These red dots exemplify the volatile points of the applications. These blue arrows represent the data that it's being transferred between the threads. And as it can be seen here in the synchronous approach, the leading thread is going to stop and wait after every calculation for a check of correctness from the trailing thread before continuing. So as it can be seen, there are a lot of waiting points. The leading thread will wait for after every calculation before continuing for a check of correctness, and the trailing thread might get to this point before the leading thread, so it has to wait for the data. So it's quite reliable, but it implies a lot of waiting points. So it's the worst regarding overhead. A totally opposite approach, it's called an asynchronous communication pattern, in which the data is still being sent and it will be verified for correctness, but the leading thread is not going to wait for that check of correctness. It's going to continue its execution. The trailing thread might detect that something is wrong, but the leading thread might have already done, especially at these volatile points, might have already done something irreversible. So especially for HPC applications that have a lot of these volatile access points, this is a risky approach. So regarding reliability, it's the worst, but regarding overhead, it's the best. And what is usually done is something in between, which is called a semi-synchronous communication pattern, in which the leading thread is only going to stop and wait at these volatile access points. And this is good regarding reliability and also regarding overhead. So this is the usual approach for a redundant multithreading approach. So as it can be seen, this inter-thread communication is a performance bottleneck. All the data that the threads need to be transferred implies a lot of overhead. Okay, so what are our contributions? We start with what we call vanilla redundant multithreading, which is a semi-synchronous approach that uses a single producer, single consumer queue in order to exchange the data between the threads. It's based on this reference, and it has a couple of optimizations regarding the queue that makes this suitable for this kind of a scenario. Our API includes 6 methods: produce and consume, the regular ones, produce and consume the volatile, and produce and consume direct, which are exemplified in the next figure. What we see at the left is the original code, at the center is the producer or leading, and at the right is the consumer or trailing thread code. What we see here at the left, it's a for loop that on each iteration it modifies a local variable. We see an MPI all reduce that takes this local variable and gathers the value in this global value, variable. This MPI all reduce is what would be identified as a volatile point. So in the vanilla approach, after every modification, there will be a produce operation on the leading thread, and there will be a consume check operation on the trailing thread. In these volatile points, there will be a produce volatile on the producer side, and there will be a consume volatile on the trailing thread. Something worth mentioning is that these volatile access points, or this MPI in this case, these instructions are not replicated. We do not want to send data twice to the neighbor or print something twice. We just want to make sure that everything is okay before continuing. So this consume produce volatile versions implies thread synchronization. The leading thread is going to stop and wait before executing this operation. And the produce and consume direct are just used to send data from one thread to the other one, because in the case of the consumer thread, this global variable value was not calculated, so it needs it in order to continue. Okay, so that is the vanilla redundant multithreaded approach. One of the optimizations that we propose is to leverage simultaneous multithreading. Hyperthreading, it's the Intel implementation of simultaneous multithreading, and what this means, what simultaneous multithreading means, is that a single physical core, appears to have two or more logical cores. And this actually means that the core actually has more architectural state. These logical cores are just basically extra architectural state that allows two or more threads to be alive, to be ready to run at the same time. And well, sadly, not all HPC applications can benefit from hyperthreading or from SNT. So we propose to use these logical cores for error detection. And what we say is that if we pin the sibling replicated threads, the leading and the trailing threads, on these logical cores, they will share the L1 cache. And since they are sharing a lot of data, exchanging a lot of data, it makes sense to have this memory close. So instead of having a configuration like this one, in which there are multiple physical cores, the same color represents the pair of sibling replicated threads, and as it can be seen, each sibling is on a different core. This is here. Instead of having this, we propose to have the two sibling threads on the same physical core, to pin those threads in that physical core so that they share the L1 cache. This is at the hardware level. The other two optimizations proposed are more at the software level. The first one is called variable aggregation, and the purpose is to aggregate multiple values into one and use this aggregated value for error detection. Both threads will aggregate the same values. So it's kind of like this. Instead of sending and receiving a 3, a 7, a 14, and a 5, we will aggregate all these values into one and just send this 29. The trailing thread is going to aggregate the same values, and it will, or it should get to the same 29. So instead of sending all this data, we can just send a portion of it. And because of the aggregation operation, if a bit flip happens in any of these values, we will still be able to detect that something went wrong, because both threads should get to the same value. The other optimization that we propose, it's more strict than variable aggregation, and it's called selective checking. And the idea is to reduce the checks to a minimum, only at the volatile points. So as I said before, the volatile points are the points where a local variable might get published or published to main memory. So what we say is that if we remove these local checks and just focus on the volatile points, we can reduce significantly the amount of data exchanged. So we don't send these local changes, and we just make sure that everything is okay at the volatile points. So this reduces the performance significantly, but of course it poses some other questions regarding reliability that will be seen in the evaluation. Okay, so the evaluation. The first experiment, the goal is to measure the performance overhead of all these approaches, the vanilla, the aggregation, and the selective checking. For that, we chose two HPC applications that are representative of what the HPC community is doing. The first one is called COMD, which is a molecular dynamics simulation, and the other one is called HPCCG, which is a conjugate gradient. The node where we run this first performance experiment, it has two Intel Xeons. Each one of them has 10 physical cores, so there are 20 physical cores, and each physical core has 2 hyperthreads, so it's 40 threads in total. Okay, so what we see here is the normalized execution time for COMD. It's normalized execution time against the non-replicated version of the application. So this first bar, for example, it means that using the vanilla redundant multi-threaded approach, it takes about 6.8 times more than the non-replicated execution. So that is a lot of time. That is a lot of overhead. These groups represent the level of optimization applied. Vanilla, it's no optimization. The second one is aggregation, and the third one is selective checking. And each one of these bars within each group represents whether we pin the sibling replicated threads to different cores or if we pin them to hyperthreads, to the same physical core. So as it can be seen, as we apply the next level of optimization, we are able to reduce more and more the performance overhead. And we can see that in all the cases, it is better to pin the threads to the hyperthreads, to pin the replicated sibling threads to hyperthreads. So in the case of COMD, we are able to reduce the overhead all the way from a 6.2 up to a 2.3. There's a big reduction. And in the case for HPCCG, we also see reduction as we increase the level of optimization applied. And we also see that in every case, using hyperthreads, it's the better idea, the best idea. So in this case, we are able to get to a 1.41 overhead, which is quite desirable for a replication technique. Okay, so what about the reliability of these techniques? How much errors are they able to detect? That is the next experiment. So in order to measure that, we have to inject soft errors. We have to inject, and we used a tool called Flipit, which is from Calum. The goal is to measure the soft error detection capabilities with all the optimizations. There is only one error injected per execution, and we have two experiments. One where we allowed errors only at the main kernel of the HPCCG app, which is a d-dot product between two vectors, and another one where we allow errors in all the HPCCG code. An error can be classified into 1 out of 5 states. If the error, if the application finishes with the expected result, we classify that error as benign. We know that it's injected, but if we take a look at the final result and it's the same as the expected one, we will consider that error to be benign. If the technique detects there is variation, we will classify that error as detected. If the application finishes correctly, but it finishes with a different result than the expected, we will classify that error as corrupted. If the application does not finish, if it crashes, that error is classified as crashed. And if the application does not finish, it's classified as a timeout. Okay, so this first table, it's where we allow errors only at the d-dot product, at the main kernel of this app. Something, well, we see each column is the level of optimization applied. And something worth mentioning is that, for example, with the non-replicated execution, we see about 66% of corrupted executions, which is quite high. We see about 30% of benign errors. That says that HPCCG is quite reliable. And if we take a look at the vanilla approach and the aggregation approach, we see that there are no corrupted executions, which is quite desirable. And this means that the error was able to detect pretty much all the errors that would have corrupted the final result. So that is why we see this high percentage of error detection. These two optimizations, these two level of optimizations are able to detect all errors that would have corrupted the execution. But if we take a look at the selective checking optimization, we see that there is some percentage of corruption. So there is less detection, of course, and there is a bit of corruption. And this kind of exemplifies the trade-off between having the best performance overhead, but it has less reliability regarding detecting errors. If we allow errors to be injected in all the HPCCG code, we see something quite interesting. We see that HPCCG in general, for the non-replicated execution, it's quite robust. We see that 91% of the time the errors do not cause any harm. And something interesting is that the vanilla and the aggregation, they have less benign percentage of errors, but the reason for that is that actually they are detecting a lot of these benign errors. So these errors that are detected in these two cases would not have corrupted the final result, but still they are detected. And something quite interesting as well is that the selective checking approach also does not have any corrupted execution, which is quite desirable, and it detects some error detections. And we see again a high value of benign errors in the selective approach. But something very important is that it has no corrupted executions. Okay, so the conclusions. This paper studies redundant multithreaded to detect silent data corruptions in HPC applications. In order to improve performance, the first thing is to leverage SMT for error detections. And we also propose two techniques to reduce the data exchange between the threads: value aggregation and selective checking. We show that selective checking using simultaneous multithreading threads have a promising result with performance overhead as little as 1.41 times, while still ensuring a good error coverage. And for the future, we plan to study the impact of these optimizations in more detail on the probability of experiencing a soft error, and we plan to study more applications. That is it. Thanks a lot. If you have any questions or comments, I will be happy to take them right now.